Okay. So my name is Travis Goodspeed, and this is my first attempt at a business lecture, which means that it's a business lecture for about 15 slides, and then I devolve into various ways to break the technology that I'm advocating. So I'll be speaking about wireless sensor networks, which are very small computers containing a microcontroller, a radio, and a battery supply, a power supply, which are truly wireless. You don't have to plug them in. You can just stick them to a wall and forget about them for a couple of years. The problem is that as soon as anything of value is trusted to these systems, their security becomes relevant. If you're just using them to monitor the weather for a high school science fair, there's no reason to attack you. If you're using them for academic research, there's very little reason to attack the network. But as soon as you take that academic network with the academic designs, which are intended to be easily debugged and easily modified, and you place it out in the field, suddenly a lot of things that weren't relevant before cripple you. Your cryptography becomes useless and other things like that. I'm also an engineer of superior belt buckles. I don't have time to just go into detail on that in this lecture, but they're quite neighborly. So the vendors in this lecture have been chosen at random, except for Texas Instruments. And I pick on their MSP430 chip because I like it so much. You've got a very good debugger in this chip. It's low power. It has all of these different advantages, and you should get a development kit for it. And if you are Texas Instruments, you shouldn't sue me. So first, I intend to convince you that wireless sensor networks are utterly essential for business, that whether you're managing a factory or an electric grid or some other sort of public utility, you'll need these because they'll save you tons of money. They'll allow you to do things with your business that you couldn't do before. But at the same time, the present designs are not to be trusted with anything important because they can be broken. So first, as an asset, I'll be going through the technology and how it's used for environmental monitoring, for landmines, and for an advanced smart electric grid. Then I'll go back and I'll describe in more detail how this technology works, what is inside of the hardware, and how to attack it. So I wrote the first Stack Overflow exploit for a wireless sensor in 2007. I presented it at TourCon 9 and the Texas Instruments Developers Conference in 2008. It was the last Texas Instruments Developers Conference, and I'll miss it. Then at Black Hat this summer, and again in Berlin, I presented a timing attack against the MSP430 bootstrap loader. This is a program that exists in permanent masked ROM on the MSP430 and can be used to program the chip after the JTAG fuses have been blown. With my attack, you can recover the password a byte at a time, making a given guess and then measuring the time that it takes to compare that password to tell how correct your guess is. At S4 Miami a couple of months ago, I presented some local attacks on wireless sensors. Given a device, how do you rip its keys out? How do you reverse engineer its firmware, that sort of stuff. And I did my Zigbee fuzzing belt buckle at ShmooCon. This belt buckle fuzzes Zigbee as you walk around and as it's performing its application. So if you happen to have a Zigbee network in your home and a belt buckle, the two will fight with one another until the batteries are dead on one side. And usually this will happen by a Stack Overflow being triggered and one of the devices getting locked in an infinite loop from which its watchdog timer does not recover. And I also wrote a reverse engineering framework for the MSP430, which takes advantage of the small memory of the device. This microcontroller only has a 16-bit address space, so you can take all of a firmware image, everything in flash memory, and throw it into an SQL database, then do queries on it, and have those queries do things like isolate functions and do call graphs and such. And because there are so few records, you don't have to worry about optimization. You don't have to do any of the fancy stuff that IDA Pro does to maintain some semblance of speed. I have a demo, and it's loads of fun. You can stick needles into a board, and you can watch packets go from the CPU to the radio. And as I'll be discussing later, the keys go in clear text across the same bus, so you can sniff AES-128 keys. But it's really boring for you to watch, so I'm going to set it up on a table sometime tomorrow, and you can come by and you can stick the syringes into the board and all of that fun stuff. So environmental monitoring is the classic application of wireless sensors. The original idea was that they would take autonomous robots, swarm intelligence, that sort of thing, and they would rip the motors off of them because robots are bad for grant applications. And so then you have these robots, but they can't move anywhere. So what do you do with them? Well, you just stick them in, say, the Alps, and then you can tell when avalanches will occur. You can tell how deep the permafrost is. You can tell those sorts of things. You can make intelligent minefields. So every landmine can have a little computer in it, and they can all talk to one another. So then the military commander can give orders to the minefield, which means that during war, it attacks the enemy better. And after the war, the entire minefield can self-destruct. Anything that's left can, say, from dud explosives, can start beaconing to be found by minesweepers. And the entire field can be cleared instead of staying around for decades to come. With AMI, every electric meter on every house in an electric grid will bill to the second. And you can vary prices based upon production cost. It costs a lot more to generate electricity during moments of high demand than it does during the base load, because you have to start turning on diesel generators and things that aren't as efficient as, say, the coal or nuclear power, which runs the rest of the time. With AMI, you can bill customers accordingly for that. And then if they reduce their consumption only during that moment of peak load, you can save considerable money, reduce electric bills for everyone, and make the world a better place. Now, there are the nodes themselves, which is what I'll be focusing upon, and there are also these base stations, which I've taken to calling totem poles. A totem pole usually runs embedded Linux, and it's connected to a traditional network, usually through a cellular modem or a 900 megahertz SCADA-type serial link. And these run Linux distributions created on the fly by their manufacturers. So your web attacks, your SQL injections, the SSH key stuff that the Debian project went through, all of that stuff can be used to break these totem poles, which are the ones that are actually responsible for collecting the data from the field units. I'll be skipping that because it's adequately covered elsewhere. But the one thing unique to this is that because each unit is usually stamped out from the same disk image, they often all have the same SSH host credentials. I discovered this when I plugged one into my laptop and I SSH'd into it, accepted the keys, changed some parameters, then plugged in the next one, SSH'd to it, and I got no authentication warning because the two shared host keys. Now, the sensor nodes usually run a 16-bit embedded operating system, which is not an operating system in the sense of a 32-bit operating system or DOS or whatever. This is just a scheduler for threads, and it's compiled into the actual application. There's only one application. It's common in embedded systems, but it's not something that you would expect coming from IT. The motherboard itself contains a radio, and usually this motherboard containing the radio and the CPU is plugged into a larger sensor board, which contains the actual sensors and the battery, external memory, and application-specific things. So if you want to design your own sensor nodes, you only design the sensor board, and then you purchase motherboards from someone else. So you don't have to worry about radio layout and the more difficult aspects of the design. You know that you can just plug that module onto your existing, or onto your custom board, perform only that piece of the design that's unique to your application and be done with it. A side effect of this is that you often don't control the code that's running on your radio. You purchase that from another firm, or you use the open source tools. Even the nodes themselves often have specializations. While they could be general purpose, sometimes you'll have pure sensor nodes with very small batteries and no mesh routing. These only transmit their own data. They never carry data for anyone else. And then you have mesh routers, which have very large batteries, usually no sensors, and occasionally they have external power. And because these do the routing, they have to listen for other units. And at the radio strengths involved, listening is often more expensive than transmitting. Okay, because they're transmitting at only 0 decibel milliwatts. If you listen for a while, I mean, how long does it take to use up a single milliwatt? I mean, what fraction of a milliwatt do you use in reception? Turns out to be 60, 70%. And the actual clear channel assessment to make sure that it's okay to broadcast a packet consumes the majority of the energy of each packet broadcast. Battery life is extended through reduced radio use and CPU activities. So you have to shut the CPU down when you don't need it. And at the same time, you have to turn your transmitter off when you don't need it. That's done automatically. When you send a command to the radio to transmit, then it powers up, then it fires the packet, then it shuts down. But when you're listening, you have to keep the radio on. So the listeners consume significantly more power than the transmitters at 0 decibel milliwatts. As you up the transmission power, the transmission cost rises while the reception cost doesn't, but we'll skip over that. They also do intelligent routing. So if a mesh router dies, the rest of the network has to heal around it. And when you deploy these things, you assume that some will die by accidents and some will be hit and some of the radio links won't work. Rather than try to map it out, you just set everything up and you allow the network itself to arrange the routing. And if it doesn't work, you just add a new node where you think the network is being split in half. So for environmental monitoring, there's a project called Permasense out in Switzerland. They monitor the permafrost in the Alps in an attempt to predict avalanches. So up here at the top of the mountain, you have a base station which talks to these nodes here, as well as ones lower down the mountain. And then you can see a home or a ski cabin or an institute or something there. The node itself is in a protective shoe on the ice. And then it has a core drilled within the permafrost. The sensors and that sort of stuff are thrown in there. And this is what's actually inside of the shoe. You've got the tiny node motherboard plugged into the sensor interface board. These are commercially produced by the tiny node firm. You purchase them, you plug them into the sensor interface board that has been designed specifically for the Permasense project. There are external antennas and all of that stuff. There's also an SD card adapter for long-term logging. And they intend the individual sensor nodes to speak to an access node, which speaks to GSM modems. Then they've got photovoltaics and all of this complicated stuff for recharging it. In hardware, it's a 16 megahertz, 16-bit MSP430 F2417. It uses an 868 megahertz Semtech SX 1211 radio. And they have sensitivity and transmissions and all of that stuff. There's also external flash, which will become important in a bit, and an expansion connector, which is still more so. This is what the board looks like. There's one expansion connector, the other is in the bottom face. CPU, radio, flash memory. The radio will always be surrounded by an antenna, and the antenna foil pattern is usually rather distinct. And then there's a chip antenna here. Now, in a traditional minefield, you can't clear them. When the war's over, they're still there. You have to run through with these mice, they use dogs, they have all of these different ways of clearing up the minefield, and many of them are prohibitively costly, and so they don't do them. So this sign's up 40 years after the war. Children still get blown up. But they're very effective at controlling troop movement. They're triggered mechanically, so you have pressure or vibration, which triggers like the grenade material and all of that stuff. And then these are posters for educating children about it, telling them to look for dud bombs and that sort of stuff. Now, in a wireless sensor network minefield, you network everything. And then the entire field takes orders. You can tell it to arm or disarm. You can order the entire field to lay quiet, not to make any radio transmissions, not to blow up. And then the enemy can roll right on top of it. And then you can turn the entire network back on, or only at the perimeter. You can lock them within it. You can do all of these tactical things because the minefield can now accept orders in the same way that soldiers can. They're also disposable, and you can order them to self-destruct. And they're hackable in that you can dig one out of the ground and you can stick needles into it. You can do all of the things that I'll be showing you how to do in the second half of this lecture. So you gain a lot by being able to do these different strategies, by being able to destroy them at the end, but you're liable to jamming, which is trivially easy for these radios, and hacking. If I take over your radio network and I make it blow up at the wrong time, it could hit your troops instead of the ones that you're trying to attack. And then this will also be necessary in the case that codes are lost. So if you deploy a field and you lose the war, afterward it'll be hacked into to clear it. Now for AMI, the idea is that in a traditional electric meter, you've got a wheel spinning around, and it measures how much electricity the house has used. You send a guy around once a month. He reads the number, reports it on a form. That form is read by the billing department, and it cascades down until eventually you get your bill. And if you don't pay it, that same guy comes out and disconnects you. With wireless sensor networks, you don't need that workforce, because you can have the electric meters transmit the billing information to you themselves. This initially started as AMR, and that was the sole advantage, that the meter guy could read it by radio as you passed your house. And then one guy could then read more meters, and eventually it will become its own network that will operate without trucks and vans and all of that stuff. You can get much finer reads. So if you say that you have a water leak, well, I can look at a graph of your water usage, and I can tell exactly when the water leak occurred, because you can get readings at each hour, and it's bidirectional. So I can bill you more during times at which electricity is more costly wholesale. This is because of what's called peak load pricing. The idea is that the price of electricity is rather constant or even reducing as larger numbers are sold, so long as you're using. Great. Okay, so the benefits are that this actually allows you to defend against certain types of fraud. Because if I have an electric meter with a wheel in it, and I modify that to make the wheel spin half as quickly, and I properly seal everything up so that the meter guy never knows, it can never be found out. I'll get cheaper electricity until that meter is replaced. With AMI, you can have advanced electronics looking for fraud. So if I try to route electricity around it, by analog means that I don't quite understand, the meters themselves can identify that fraud. If the meter is disconnected for a while and then reconnected, you can recognize that the wheel was only spinning during daylight hours, and then at night it was disconnected and I got free electricity. It can also detect supplier demand, supplier fraud, in that you can identify when you purchased electricity. You can identify when it was consumed. So the distributor knows exactly how much should be paid for it, whether it was peak load, whether it was base load, that sort of thing. It allows for conservation. You can save kittens and koala bears and all of that fun stuff by using less electricity. And it allows for demand response. So you can defend yourself against what's called the Christmas light attack. And not an attack really so much as a threat. What happens during a bathroom break at the Super Bowl? Everybody flushes their toilet at the same time. And the water grid sort of freaks out a bit because suddenly the pressure changes drastically. Because the pressure is reducing, nothing breaks. In the case of electricity, what happens when every massive Christmas tree light, or Christmas light installation switches on by its timer at the exact same hour? Well, the load jumps, and it jumps significantly. With demand response, you can automatically recognize that demand is spiking, and you can ramp up generation to match it. Because you have a recording of demand in individual neighborhoods, in individual houses at important times. And you can also do self-healing. So if a tree falls and it cuts a particular expanse of electric wiring, well, the electricity can be routed around that. It can go by a different path, which is perhaps longer. And because there's a difference in length, you can't simply bridge them together because one would be out of phase with the other and they'd short circuit. But if you disconnect one and then reconnect the other by computers and switches on the tops of telephone poles, you can automatically repair things. So in the case of environmental sensing, I'm not sure exactly what you could do for malicious means with it. I mean, you could falsify results, you could do mischief, you might be able to fake an evacuation. But landmines are obvious. You can take over a minefield, you could detonate it early. It could be very, very inconvenient in battle for one side or the other. And for AMI, you can facilitate fraud. You can just patch the firmware of your meter to have it bill you less. You can also misroute and maybe cause some equipment damage. And that would not be neighborly. Now, the totem poles themselves, they're computers as you see in IT. And they run services as you see in IT. They have an HTTP server. Usually it has a local SQL server. So you'll have Apache and Postgres in embedded Linux in this device collecting sensor information. And in the smaller systems, the administrator will actually go to that web interface to view the results. So you can do SQL injections, you can do cross-site scripting, you can pop out the disk and change its content to then attack the browser. You can do all of the fun stuff that you do in IT. And these are rarely updated and they're rarely given proper, unique SSH host keys. I was playing with one unit and I found, so you take it out of the box, you connect through its web interface, and you log in with the username root and the password root on the web interface. And then you change that, and it tells you to change that. What it doesn't tell you is that you haven't changed the SSH or the Unix password for the root account from the word root. Nor have you changed the Tor account or its password from Tor, which is also user ID 0. Nor have you changed any of the documented SQL administrators, nor have you changed any of the undocumented SQL administrators. So you have to significantly navigate this thing just to figure out where all of the accounts are to disable. But getting to the sensors themselves, this flash here, if it contains any secret information, is forfeit. You can stick a needle in there, there, and there. It's 3 needles, data in, data out, and clock. and you can replace the contents of that flash. The radio connects over the same bus. It's called SPI, or the Serial Peripheral Interface. And if you stick the same 3 needles in, and because of the chip enable stuff, you can actually stick them into the same spot to watch both flash memory and the radio, you can see everything that's said between the CPU and the radio. Now, what do you expect to be said between a CPU and a radio? You expect packets to be sent across, channel hopping, tuning, that sort of thing. On the chips that support cryptography, the cryptography is implemented in hardware in the radio. If this were a ChipCon 2420, which is a more popular Zigbee chip, you could catch its AES-128 key just by sticking these needles in. And because you have to have that key loaded before you receive a packet, you have to share a single AES key among the entire region. So if you capture one node and you stick a couple of syringes into it, you're able to sniff packets and craft packets for anyone on the network. And there are no hardware-enforced MAC addresses or anything complicated like that. You can just broadcast anything you damn well please. Now, the SX1211 is what I call a custom radio. It's unique to a chip manufacturer. When you purchase it, you're locked into that manufacturer, but the chips are usually cheaper. They also lack integrated cryptography, which is a good thing because it forces cryptography to be done in the CPU, and it's a bad thing because quite often they won't implement cryptography in the CPU. It's available in, these types of radios are available in different frequencies, which vary by jurisdiction. If you're in Europe, you do 800 megahertz. If you're in America, you use 900 or 2.4. 433 is available with a license. Then there are the standard radios using IEEE 802.15.4. This is an industry standard for PHY and MAC layers. Usually they will adopt the PHY and then create their own variant of the MAC. It uses carrier sensing, which wastes power, and it has on-chip AES-128. Further, it uses electronic codebook mode. So if I say howdy, and that comes out as 3F4 whatever, the next time I say howdy, it also comes out as 3F4 whatever. And because these packets are limited to 128 bytes, well, am I going to put a counter in there? And if I don't have a counter in there, every time I say howdy, I'm sending the same bytes, which means that you can watch traffic and come up with a dictionary of words that I've said. You don't necessarily know what they mean, but you know how often I've said them, and you know how I've said them in temporal proximity to other ones. Okay, so if I'm giving a temperature, for example, okay, I'll have my range of temperatures, and you can graph that out as a bell curve, whatever the distribution is. Then, as I'm broadcasting temperatures, you can map the frequencies of each packet, and you can identify that some things are routing information or whatever, but that this message means howdy, my value is this, and this message means howdy, my value is that. You won't know exactly where the center is, but you can figure it out. Further, because, say, in an indoor environment, you'll have either an air conditioner or a heater. And when it switches on, the movement of the temperature changes abruptly. From that abrupt change, as opposed to the gradual change, you can figure out which way is up and which way is down. So in a lot of the naive implementations, even with cryptography, you can work backward to figure out which certain values are, and then you can start jamming me and broadcasting your own values as if I said them. There's usually an expansion connector on these boards, and if you're trying to, say, sniff the SPI bus or tap into a serial port, it's a lot easier to use this connector than to stick syringes into the board. In this case, the second serial port, this would be TTYS1, if Linux could run on the chip, as well as some analog to digital converters, so you can make like a little extra sensor, an extra temperature sensor, a light sensor that would plug in here. You can send that UART to your PC. TinyOS, the operating system recommended for these chips, uses the second serial port, the D1, to ferry packets over to a PC, and it also uses it for bootloading. If this uses it for bootloading, and if you also control the TDI and reset pins, you can flash the firmware through these two pins, 3 and 5. This is the radio, and you'll note that all of this stuff in the top right gets routed into a single bus, and that bus goes out to another board from the schematic. That's the digital logic connections, chip enable and data in, data out. Here's a closer view. So MOSI is master out, slave in. That's how the chip receives information from the host. You've got clock, you've got interrupt pins, because interrupts have to be handled manually on these devices. You can't just let the operating system take care of it for you. You have to know which wires are being raised to start these interrupts. You're also given a standard layout, and you can see these same pins. If I go backward and forward, these pins here become these pins here, which are routed off of this board to the controlling CPU. And if you want to stick some needles into it, and I actually use hypodermic syringes for this, you just stick them in there. You don't need all of them. You just need MISO, MOSI, and clock. This allows you to do convenient radio sniffing. You don't need to figure out the channel hopping pattern. Okay, so instead of having to have a fancy radio that can tune in advance of the change, all you have to do is stick some needles in, and then you can actually see the command telling the radio to hop to a new channel to listen to it. And if it then tells the radio to shut down or to remain in low power mode, you can override that. You can inject a new command, tell it to listen all the time, because you say, don't worry about its long-term battery life if you're tapping into it and using it to hack the rest of the network. You can easily distinguish a reception and a transmission without having to fuse signal strength and worry about amplifiers and all of that stuff. This is important when you have a very strong signal being sent out to sensors that broadcast rather weakly, because the stronger signal might actually be further away. And then on keys with hardware cryptography, you can watch those keys be loaded in the clear. You can also do radio simulation. So you lift a pin of the real radio, or rather you cut a trace in the board because the radio chips don't have pins. Then you can create your own radio using a USB peripheral or an FPGA. And you can have fake packets go back and forth. So if you're trying to do an attack that requires lots of, say, dictionary samples, you can set up a fake radio, do the attack on the captured node, and the rest of the network never has to know about it because you've taken it over. This is the Total Phase Beagle, which is the sniffer that I like. And Total Phase writes the most neighborly cease and desist letters I've ever seen, asking for my Flickr images to be taken down. And then there's the Aardvark. And if you compare the designs of the two, it was probably my annotating the chips that got me the letter. Let's see. Yeah, this is a very high-speed USB to serial chip, and this is a Xilinx CPLD loaded by this flash chip. So, because the same things are relevant on these designs, you can copy this device by copying its schematic and all of that stuff, and then dumping the firmware out of this chip, which is not capable of protecting it. I think. It's been a while since I've looked at this. And then the Aardvark just has an Atmega 16 sitting here in the middle, a slower USB to serial chip there, some flash memory, and I/O on the side. The Beagle is used for sniffing packets, and it's the best device in the market for it. The Aardvark is used for adapting to the bus. So if you want to forge a packet, if you want to talk to a radio directly, use the Aardvark. Or you can use the Hackaday Bus Pirate. which does the same thing, but it also supports a lot of extra protocols. So if you want to get into this and you want to purchase tools, buy the total phase stuff, but also build yourself a bus pirate. They're neighborly. Now, another important thing to cover is the difference between JTAG and bootloaders. When you have a PC, you have a little bit of ROM, which bootstraps the rest of the system from disk. It knows enough to start copying information from a hard disk or a USB disk or whatever source. On a microcontroller, you don't have that issue because you've got flash memory mapped into RAM, or into the memory bus. Okay, so you can just fetch a piece of memory, and all of the programming, even though it's reasonably permanent memory, is mapped onto the memory bus, and it can be dereferenced as a pointer. You can execute it directly. You don't have to copy it from elsewhere, except when you're first programming the chip and when you're doing a field upgrade. Now, there are two ways to do it. First, you can expose the hardware of the chip to the outside world. Allow the programmer to single-step it, allow him to read and write anything in memory, allow him to debug the system. This is great if you're trying to build a device. It's great if you're trying to program it, but it's a bad idea once you're distributing these devices, because if I'm trying to reverse engineer your device and I can just stick in a single connector and then single-step your device and debug it and dump all of its memory, it's very easy to clone the device. So this is disabled by a fuse. In the case of some chips, it's an EEPROM cell. In the case of the MSP430, it's actually a physical fuse that pops. And once it's blown, it's very difficult to repair it. You have to remove the lid of the chip and then physically repair that connection. And I don't yet have the tools to do that. So instead, I attack the bootloader, which is implemented in software, and the older versions can't be disabled. So there's a reset sequence that I can send. If I twiddle the test pin as I'm resetting the chip, instead of starting at the reset vector of your application, the chip will instead look at 0xC02, and it will jump to the address that it finds there. And that's a program that exists in permanent masked memory. You can't change it, you can't erase it, you can't patch it. And it defends the contents of memory by a password. So I built this little gizmo to crack that password. In the center, there's an MSP430. I use the chip because I love it. And over here is the 74HC4053 analog bidirectional mux. Satellite TV hackers would use this to unloop TV cards. Okay, so if DirecTV or Dish Network or whomever disabled a card, they would use these muxes to glitch the power that went to that chip. You drop VCC low, you raise it high, and you can skip the write-back phase of an instruction. So my device does two things. First, it does a timing attack of the password comparison. This gets me about half of the MSP430s in the market. So I measure the password comparison, and I do a weird serial port trick to make sure that it never waits on an incoming byte. Because if it waits for even a single cycle of a while loop, then I've lost whatever timing information I hope to measure. Afterward, I measure the comparison delay, and that will vary by 2 clock cycles for every correct byte. Now, in the voltage glitching attack, I drop and raise the voltage. And the victim's transistors glitch, but they don't glitch altogether because you've got propagation delays. Okay, so whether it's the instruction decoder that fails or the memory bus that fails or any number of things, I don't care so long as it skips over the write-back phase of the jump instruction. And this takes me a lot of tries. The device will sit there and attack the victim 1,000 times before it falls in. I'll get to why in a bit. But this can be used to drop it into the bootstrap loader even after it's been disabled. So if you turn the bootloader off, I can get into it anyways. And then because you assume that it can't be enabled, you might use the same password on every device. So in the case of some things are missing here. In the case of the timing attack, the attacker sends a synchronized byte, it's 0x80. The victim replies with an acknowledgement, and the attacker guesses a password in this region here, and then the victim replies with a NAC, saying the password's wrong. This is the delay that's measured. The bootloader exists in masked ROM, which is mapped from C100 to 1000 hex. And like any executable code, you can dump it and you can reverse engineer it. I've printed out the disassembly of this for several different revisions, and then I run through with a pen and I mark it up, like what this function does, what that function does. Because there are so many different chips, I've got lots of different revisions of these. And now I've done it so many times that I can annotate this in a couple of hours. And the password itself isn't just a password, because you have to take memory efficiency into account, and you have to take into account that the compiler vendors would probably screw up any custom password or anything that was only a password, because that's not essential to execution. So the password is shared with the interrupt vector table. There are 16 interrupt vectors, which are 16-bit pointers to interrupt handlers. The chip looks at one of these addresses, and then it pushes that into the program counter whenever, say, an I/O pin raises high or a byte is received over a serial port. So even though this is 256 bits, this paper by Becker and a few other German students estimated that at least 40 of them were random, and then they came about with the number of 128 years for brute force. I figured out how to reduce that to 32 by overclocking the chip. You can actually send it an overclock command, but I don't have time for that today. So if these are the 256 bits, one cell per bit, they're all the addresses of valid instructions. Every instruction is even aligned. So that entire right column is composed of zeros. Further, the reset vector always points to the first word in flash memory. Of all of the images that I've looked at, there's only one exception to this, and that's a TI product with a weird bootloader. It actually causes the product to break if you give an update intended for one to the other, because they hardwired the entry address, but it's another story for another time. Also, whatever interrupts you don't use all point to the same address. So depending upon your compiler, all of these are either the same entry or they're just zeros pointing that it's unused. And then you only use so much flash memory, and it's allocated from the bottom up. So if your program is only 4 kilobytes, you're not going to use any flash memory higher than that, so I can guess at the high addresses. So these 40 bits here are the ones that are actually hard to guess. And they're only hard to guess if I haven't seen another program in the same series. So if you forget to blow a JTAG fuse for your prototypes, and I steal both a prototype and a production unit, I can guess the production unit's password by going back and just assuming that some of these are similar and guessing at these lower bits. Now, I ran the password comparison routine in simulation. So I had a very simple program. You'll see how simple it is by its password in just a second. But all it did was wrap the password comparison routine. If you look at the routine, in the vulnerable versions, there's a jump instruction which skips over a bit immediate set if the bytes match. It takes 2 clock cycles to go left, 4 clock cycles to go right. And then I do an entry and exit and all of that fun C stuff. And the nice thing about running things in a simulator is that you can change arbitrary pieces of hardware. I mapped the bootloader at the same address, but I mapped it as RAM. So I could just change individual bytes, link everything together, and handle it by script. When I got my simulation results, it took these many cycles to try each individual byte as a repeated password. Say all zeros, all ones, all twos, all the way up to all FFs. If we take the difference and we divide it by 2, it tells us that the password will have a single 00 in it, 16 11 hexes in it, and 15 3As in it. And sure enough, this is the password. So 1100 is the first word in flash memory for the chip that I'm simulating. And it will always be 1100 from every GCC firmware image that's spat out. The others are all 3A because they point to a dead handler function that just recognizes that an interrupt that should not have been called was called. If you look at it on a scope, it's the difference between these squiggles and that squiggles. And if you manufacture 1,000 units from the same firmware image, they have the same interrupt vector table, and they have the same password, which means, just like with the SSH keys and the totem poles, that if I take one and I send it to a lab and I go to the ends of the earth to break it, I then have the keys to the kingdom and I can steal any other, break into it through a serial port in the blink of an eye, and I can read keys out of it. This mechanism was only intended to prevent plagiarism, to prevent you from taking your competitor's product, ripping the firmware out, sticking it into a compatible board, and calling it your own. They never intended for these chips to store cryptographic keys. So their bootloader doesn't defend against it. Becker had similar feelings about it. He demonstrated that it was infeasible to brute force this password. So he assumed that either you could break into it by other means, in which case your password choice wasn't terribly relevant, or you couldn't, in which case it didn't matter. So if you search for Becker on my blog, you'll find a script of his that I've published. It takes the interrupt handler. So if at FFE0 you have the word 1100, meaning jump to 1100 hex when the chip turns on. And that goes to a handler function at 1100 hex. His script will instead pick a random unused word of flash memory, a pair of words actually, and it will put a branch to the real handler function in it at the relevant address. So the password then is unique to each firmware image that comes out of his script. So on your assembly line, you can run this script on each password, or on each firmware image to scramble everything, to make the passwords different. And then the attacker can't simply rip out of one as he did the others. The way voltage glitching works is that in this CMOS inverter, we've got a pull-up transistor and a pull-down transistor. If the input here is 0, then this conducts. If the input here is 1, then this conducts. So if you get a 0 as input, you have a 1 as output. A 1 as input gets a 0 as output. But these are real voltages. And if I drop this high voltage here, then this ceases to conduct, then this Q becomes less of a 1. And that will spread to the next piece. But because chips are designed to be resilient, this doesn't actually break anything. This doesn't cause the chip to reset. And if you hit it at the exact moment that it's overriding the program counter at the end of a jump, you can skip that jump. So in the case of the bootloader, if you disable it, you've got this value at this address, and then even if the interrupt table is known, access is denied because you can't start up this bootloader program. But it doesn't actually reset the chip when you try. Instead, it sits in this infinite loop here, this JZ plus 0. So if the Z flag is set, it spins for all time. Eventually, the watchdog timer resets the chip, and it jumps into the intended application. Now, it takes 2 clock cycles to execute. And I don't really know whether it begins in a rising or falling edge, but I'm assuming rising for the purposes of the story. On the first edge, it adds 2 to the program counter. On the second edge, it replaces the program counter. This happens in the first clock cycle of every instruction. Then, on the third edge, it adds 0 to the original program counter because that's our offset. And then on the falling edge, it replaces the program counter. If you skip this edge here, if you make it not successfully overwrite the program counter, if it overwrites another register instead of R0, then the JZ instruction falls out of it. It's as if the Z flag were clear instead of set. And that lets us into the bootloader. And afterward, this comparison is never performed again. Nowhere else in the code does it make sure that the bootloader is allowed, because they already checked once and they assume that the first check is sufficient. Also, because this jump is being run 1,000,000 times, there are a lot of chances to glitch it. So even though you don't know exactly when a clock cycle occurs, you can guess, and you'll be correct soon enough that it will fall in. The code that I use to exploit this is ugly as sin. It's a terrible hack that I threw together in a couple of minutes, and as soon as it was working, I started screaming and running around, and I stopped development on it. But it shouldn't be this easy to break into it, yet it is. With any luck, the newer chips will defend against this, but not so sure. The only difficulty in glitching it is actually knowing when to cut the power, because you want to catch just that 4th cycle. In the smart card glitchers, they would count clock cycles. So the attacker controls an external clock, which is being fed to the victim, and then he just counts cycles until he's at the one he wants, and he cuts power at the exact moment of that edge, or an offset of that moment. But the MSP430 has an internal clock, so you can't simply feed it your own custom clock and have it fall victim to that. And this is a scope diagram that from an experiment of mine, where I'm using power analysis not to figure out what the chip is doing, but when it's doing it. CMOS only consumes significant amounts of power during a switch. And switching predominantly occurs on a clock edge. And this is a very power-efficient chip. It doesn't use any electricity that it doesn't have to. So every time a clock edge occurs, there's this drop in voltage as the chip consumes electricity and performs work. So by extracting this signal, it should be possible to also extract the internal clock. Then all you have to do is figure out the offset from that you want to glitch at, and count clock cycles just like you would attacking a smart card. And these are vulnerabilities that are found within a chip. So if I open up a design of yours and I find one of these chips, I then know that the vulnerability is applicable to your design. And also, you can't patch prior shipments. In the case of design mistakes, you can't even patch new shipments because it'll break backward compatibility. If you're buying widgets from me for your mass production, and a massive production run fails because you developed on revision A and I sold you 100,000 units of revision B, which fixes a security flaw but also breaks your product, you're not going to be terribly happy with me, and you're not going to purchase my chips in the future. So disclosure becomes an issue because these things can't be fixed. When do you talk about them? They have errata sheets for announcing bugs. So for every chip that you might buy, you can look up the errata sheet for it, and the manufacturer will tell you, oops, we screwed up the synchronization on the second analog to digital converter. If you use it at rates above this, expect wrong readings that look like this. But they don't include security bugs there. If you look up the MSP430 stuff, you won't find any of the BSL vulnerabilities listed. It's not like IT security where you have disclosure lists and bounties and all of that other stuff on it. Now, field upgrades are also really, really hard. Because if I cut you off in the middle of a field upgrade and you don't have enough memory to store both the new firmware and your old firmware, then I can kill you. Because in this little gray hour, you can't operate. At the same time, you have to verify the upgrade cryptographically, which means that you have to know that no piece of the upgrade has been swapped out. This also involves asymmetric cryptography, which is expensive to implement, and very little of the reference code will work on 16-bit machines. You also have to worry about key distribution, modes, and all of that stuff, because when you use, say, electronic codebook mode, you expose yourself to vulnerabilities of replay and such that the embedded system designers were never trained to think about. You also have to worry about physical security, where you wouldn't have to do so as much in IT. How often have you had to worry about someone popping one of your computers open, sticking needles into it, just to steal a cryptographic key to use elsewhere? So it's handy to have tamper protection and tamper resistance methods. And one of the most effective I saw was actually an epoxy block around a radio used by the French water metering system for Paris. They just dripped epoxy into the plastic case. And then if you wanted to forcibly extract it, you could take it home and you could stick it in an oven or you could chip away at it. But there wasn't much that you could do on the scene. And this slows down an attacker dramatically. If the attacker has to be on a controlled site to attack the device, that could be very effective. In the case of the water meters, not so much. It was probably for reliability and that the epoxy would prevent water from getting to the circuitry. But I don't yet know. Also, there are some easy things that you can do, like blow the damn JTAG fuse. I've had multiple conversations that go like this. Like, howdy, we just found this chip number. Is it vulnerable to your timing attack, and can you rip out the firmware for me? And I say, sure, neighbor. And then they say, never mind, the JTAG fuse isn't blown. We can just plug up and rip everything out of it, patch it as we please, and stick it back in. You can also randomize the bootloader password using the Becker script. And do it even if you're disabling the bootloader password. So I'm not sure how I'm doing on time. So I can take questions or I've got more slides. Which would you rather see? How am I doing on time?
You've got 10 minutes.
10 minutes, okay. So you can do photovoltaic glitching. When I was first experimenting with the glitching attacks, I had to determine whether or not the chips had booby traps, which would identify that they were being glitched and lock up or reset or perform something like that. I had to do this because when I guessed a capacitor value wrong, I would lock up or reset the chip. And I had to know whether this was a self-defense mechanism or an accident. And I was reading about Sergei Skorobotov's use with shining a laser down a microscope to hit a single SRAM cell. And then he watches the power consumption of that SRAM cell, and that tells him whether there's a 0 or a 1 in that cell. I don't have the equipment to do that. But what I do have is a camera and some friends with acids. So I got a decapped MSP430, and I ran the chip under a debugger, and I hit it with a camera flash. So this is the chip. This is actually the picture that first did it. So you take the camera, snap the flash, and then this paralyzes the memory bus, but it doesn't reset the chip. You can see in my debugger, I'm fetching FFE0. It's beef, it's beef, it's beef, it's all Fs. And even though light can clear flash memory, this hasn't really been cleared. It just looks like it's cleared because the memory bus has been frozen. If I could get this to only do flash memory and to not do masked ROM, then I could run a program in masked ROM, hit the memory bus to make the password appear as all zeros, do my password authentication, wait a couple of hours or days for the charge to dissipate, and then I could run back and dump all of memory. But in this case, the only useful thing was that it told me that there was no self-defense mechanism from glitching. Because when I hit it with the flash, that freaked out every circuit within the chip. I don't have a screenshot of it, unfortunately, but one of the other effects I got was that every read I made would return the value stored at the previous address that I tried to fetch. So like if after all of this, my next one were XH 0x dead, it would instead return beef, returning the value of the previous request because there was a latch that was flipped the wrong way. There's MSP430 static, which is like IDA Pro, but for taking apart microcontroller firmware. Because all of memory is so small on this chip, you can shove everything into an SQL database and then do unoptimized queries on it. Just jerry-rigging SQL queries and little Perl functions. And with SQLite, you can easily expose any Perl function to your database because they run as a single process. So then you can come up with new SQL queries and do all of that fun stuff. And I also manage libraries and hashes and stuff. So in this case, if you want to help out with something and most of your experience is in Unix or Windows, help me reverse engineer some linkers. The idea is that when I rip a firmware image, when anyone rips a firmware image, there are lots of different compilers and libraries. And the standard libraries are given away for free by the compiler vendors in the 16-day trial or 4-kilobyte trial versions. Everything is statically linked when you load it into the chip. There are no debugging symbols that will ever be found within an MSP430. But because the libraries ship with compilers, you can dump them, and then you can compare fragments of code for equality. It's really easy to identify where a function begins and ends in an MSP430, because the return function will always be after the last target of a relative jump. It'll be the first return after the last target of a relative jump. So having found a function, you can then search a database and see if that function exists there. This is the absolute value function from ImageCraft compiler version 7 for the MSP430. You'll note that you have Unix on the outside of the record and DOS on the inside. That's because they purchased an assembler and a linker written for DOS. So this would be \R and C. Now this S record here tells us the name of the function. It's an absolute value. T tells us that at an offset of nothing, if there were multiple T records, you would have this 16-bit value counting upward. You have this machine code. 3041, or 0x4130 in Big Endian, is the return instruction, and this will end the final T record of every function. So you can split this apart, and you can you can disassemble it, and you can see how it behaves. And a point of interest, this code here, E03E FFFF, does a XOR of FFFF on R14, or it inverts all of the bits. You can do that shorter by using E33E. This is a bug in the assembler, and you find a lot of these when you start taking compilers apart. Now, while I can use one of them, and that's fair use because I'm just showing you what a bad compiler it is, and free speech protects you when you're complaining about something, it doesn't protect you when you're taking large amounts of code and repackaging them and shipping them to people in electronic forms. But I don't really want to give you the code to be able to link into your own program. All I want to do is to allow you to recognize that you have the code when you do already have a copy of it, and I want you to be able to know its name. So instead of storing the actual contents of the function, I instead store the MD5 hash of the contents of the function. So if you don't have this function, if you're trying to pirate the absolute value function for the MSP430, it's very difficult because you've got this one-way hash. But if you need to identify what a function is, you just take its hash and you search my database for it. And I ship this database with MSP430 statics. If you're trying to identify any ImageCraft or GCC application, you can easily do so. And there's this macro function, .symbols.recover.
Hi.
Howdy. Which, and all you do is you say update funcs, set name equals this, where MD5 hex equals that, in such and such. And even though this isn't terribly efficient, it runs in the blink of an eye. That's the beauty of it. You can write really ugly SQL code that's terribly inefficient because you have so few records in memory. Now, I've only reverse engineered the ImageCraft format. The GNU format is open. I don't yet have scripts for dumping IR's compiler, TI's compiler, the Crossworks compiler, or all of these weird one-time use compilers from companies that have ceased development. So if you'd like to help with this, email me and I'll point you to the free demos and you can have at them. And I think that's my real last slide. So thank you kindly, and do you have any questions? All right, thank you.